Okay, so we'll continue today talking about hierarchical models. And we left off last day talking about a hierarchical mixed model. And I want to jump back into that project to illustrate a couple things. So we'd started with hierarchical models doing a scenario where you had within subjects manipulation of condition A1, B, or A2, and then outcomes were binomial, but you had a whole bunch of outcomes for each person at each level of A1 and each level, well, in A1, as well as a whole bunch in A2. And then we extended to hierarchical mixed binomial, so you had both within subjects manipulations and between subject manipulations, but still for each combination of cells in the design and person, you had a whole bunch of observations, and it was binomial. Last class, we moved on to when observations are Gaussian, not binomial, and the only sort of elaboration that needed was instead of expressing the model as having a Bernoulli-Logit relation to the data. Here we're expressing that we have a normal distribution relating the parameters to the data with, and therefore with a normal, you talk about the mean, but you then also talk about some sort of measurement noise. I wanted to start out today taking a look at how this differs in terms of the outcome from just collapsing the data to means per condition, and then just doing a mixed design, which we had before. So let me pull up the teaching. I think it was like mixed, yeah. All right. So mixed long is what we had. So I'll pull up that mixed long. Oh, no, I won't. And if you remember, the mixed long was the one where you had this function at the top which got the coefficients given a person's data and within subjects predictor matrix. So instead of us having a hand code, okay, this person's intercept and this person's difference between conditions, it does all that for us. It also has the ability to do between subjects design, so it incorporates the between subjects predictors. But again, the way the mixed, this repeated measures within subjects, non-hierarchical models worked. You just had one observation per person in each condition that's manipulated within subject, whereas the hierarchical version has multiple observations per person per condition of interest. One nice thing about the hierarchical model that I hadn't mentioned the other day, but it actually naturally incorporates imputation of missing data. That is, we previously, when we used the mixed long, if there were any missing data, we had an issue. So we had this extra thing, mixed long missing, that we went through, and that allowed you to do special imputation for missing data. So you would have somebody's data coming in, and there'd be like an NA in one of the conditions where you were supposed to have a measurement. With the hierarchical model, you can just have absent data for a given person in a given condition, and the model will be is naturally going to still estimate out for that person the coefficients that we normally would have had to add some imputed data points to get out an estimate for the coefficient for that person. Here it's just doing it automatically, so it sort of incorporates missing data imputation by itself if they're missing data for like all the observations for a given condition, if that happened to be missing at random for some reason. Now, hierarchical tends to occur in the scenario where you have data collection designs where you're trying to make lots of observations per condition, so it's a little less likely that they'll be missing at random from a given condition all the observations. But it can happen, and the nice thing about hierarchical models is they automatically do the missing data annotations. So if somebody is missing data, you don't have to toss them. They still have information to provide about other parameters in the model that help improve your power by including them. All right, so I've got that mixed long. Actually, I'm also going to grab the mixed long. Oh, no, it's not in there. Thought it might have already been compiled. So I'm going to load up. I'm going to make that a little bit smaller. Load up standard packages, including the new one, EasyStan. Read in this data. Guess I'm not going to bother adding the sex column. Well, fine, I will. So again, this was just making up a variable. I don't. Because it's made up, I don't really expect it to have an influence on the outcome variable. We could do some visualizations of the data. Just to remind you, we've got some outcome that's relatively, well, it's continuous, so we might want to make an assumption of Gaussian distributed error. We've got two conditions, A1 and A2, and an observation, a bunch of observations per person in both of those. Can look at the distribution of observations across people, so not differentiating A1 and A2, and this will eventually come up with a plot. There we go. Not enough observations to really talk about whether any given individual has normal or non-normal data. I happen to know that I generated the data artificially, and these are all normal, so even something like this is possible under normally distributed error. Just random sampling. We did some other things the other day where we looked at, okay, and actually by hand went through and computed the mean for each person and the difference between the values in A1 and A2 for each person, etc. I'm just going to skip all that. So the workflow we had to do the hierarchical model is as follows. You make sure that things were arranged by ID. They already were, but that's okay. You express what the within subjects model is and get the corresponding contrast matrix. So for each row in the data set, you get a matrix or a set of values. One for the intercept, of course, and the other one is just coding which level of A that row corresponds to. So then we need to reduce the data down to one row per subject, and that allows us to get out what the between subjects contrast matrix is. So we've got this dummy variable sex that we're pretending that we actually care about. Say if you actually didn't have any between subjects variables, you can still use the mixed code. I mean, it would be technically a little bit faster to use the purely within subject code that I gave you, but if you don't want to keep juggling multiple stand files, you can just use the mixed code if you don't have any between subjects variables. So in which case you just express the formula as tilde1. That just means that it would have just the intercept column in that model. I'll show you in a moment if you don't have any within subjects variables or predictors, in which case you just have a hierarchical between subjects model. I'll show you that in a moment. But for now, we're sticking with this mixed design. We've got the within subjects matrix and the between subjects matrix, where, again, it's just one variable, so it's just coding for what sex that person is. And this is already being compiled, so hopefully this runs. We tell it how many subjects there are, how many observations there are in total, how many predictors, within subjects predictors there are, how many between subjects predictors are. We give it all the outcomes, we give it the within subjects predictor matrix, we give it the between subjects predictor matrix, or contrast matrix. And we give it a list of, for every outcome, y, what is the subject that goes with that outcome. And we do this as numeric factor bit to ensure that whatever was in this ID column gets turned into a set of numbers from 1 through however many people there are, so that this S can serve as like an index. It runs through. Maybe while that's running, I'll pull this over. And again, it's going to express that, well, it's internally transforming the data. It's going to express that there's some set of population means for each of the coefficients. So if it's a mixed within and between design, there's going to be as many rows in this coefficient matrix as there are between subjects effects, and as many columns as there are within subjects effects. The first row of this matrix is going to correspond to the main effects of the within subjects effects, and then subsequent rows will correspond to interactions with the within subjects effects. These get all renamed in our, thanks to the easy scan afterwards. In the model, we're saying that, again, people vary from one to another on each of the within subjects coefficients. So people are going to vary from one to another in their intercept. People are going to vary from one to another in the degree to which A has an effect. If there were other predictors in the model, we'd have further things, but there's just 2. So this SD quantifies that variability. There might be correlation amongst those variabilities. So somebody with a high intercept might also have a high A effect, or conversely, somebody with a high intercept might have a low A effect. So we model that correlation. Critically, we're not expressing anything about the different groups as specified by the between subjects predictors having anything different about how they vary or how the correlation manifests. That's a pretty standard assumption that, it's a simplifying assumption, so I can imagine more complicated models that allow them to have different variabilities and covariabilities, but I've actually never seen those models used or published anywhere, so it's okay to be a little bit, to have that somewhat restrictive assumption that the groups, like your between subjects effects, don't affect how the groups have different variabilities and things. We create a little matrix here that's going to store for each subject what our estimate for that subject's intercept is and for that subject's A effect is. And we also, again, because this is Gaussian, we're assuming Gaussian error on our measurement, we need to express like the magnitude of noise that we think might be in the measurement. So noise lower bounded at 0. Express a prior on the coefficients as they're all just normal 0, 1. Express a prior on the variability. So Weeble is pretty reasonable for that. Flat prior on the correlation, and a Weeble prior on the noise as well. We say that each person is sampled from a multivariate normal distribution with a set of means as defined by what the sort of population coefficient means are, as multiplied by what the between subjects coefficients are for that person. So if there's an effect of the between subject coefficient on any of the within subjects predictors, this works that out. This also, because this includes the intercept, this will work out, of course, if there's a between subjects effect on the intercept. And we've got the covariance matrix being built up here from the standard deviations and the correlations. So having gotten out for each subject, given what group they're in, the coefficients, the within subjects coefficients that correspond to that subject, You can then loop over the observations and say for each observation, we're expressing a model where the observations have a normal distribution with some amount of noise, notably the same amount of noise no matter who you are and no matter what group you are, with a mean centered on, well, this little bit figures out, given the current subject, that's subject I, and the current contrasts for that row, so for that observation, what within subject conditions does that correspond to? Figure out what the mean for that condition should be. So that's what that little bit does. And that's actually explained a little bit in more detail down here. Yeah. We then have a generated quantities where it figures out the unscaled versions of the things that we're interested in, the coef means and the coef SDs. We might be interested in noise. I guess I didn't add that in there. If you wanted to get out the unscaled measurement of the noise, because technically this is scaled noise. But we can go back and take a look at the output. Take a look at these counts. They're all small, so we can ignore them. We can look at the posterior for the noise. Now this is Z scores, so if I were to redo this, I'd make sure that there was an unscaled version of the noise, but ranging from we're pretty certain it's somewhere between 0.64 and 0.68 Z scores, which is actually fairly noisy data, because if the entire data set has a standard deviation of 1, we're estimating noise as being sort of a rather substantial proportion of the data. We can look at the coefficient means, and by using stand summary and giving the two contrast matrices used, it gives us these nice names for things. So main effect, or here's the intercept, main effect of A and its credible interval, main effect of sex and its credible interval, and the sex by A interaction and its credible interval. I'm going to actually copy this because I'm going to do a comparison. So put it in a new file. And we can do a bunch of other stuff, which I'm not going to do. I just want to stop it there, and what I'm going to do is dat2, I'm going to pipe to, so I'm going to group by ID, sex, A. So value equals mean value. Oh, sorry. Dat2 doesn't exist yet. I want to pipe dat through this pipe and store the result as dat2. So if I say view dat2, we've got 2 observations for person 1, 2 for person 2, 2 for person 3, etc. So this is more the format of what we were looking at before we got into hierarchical models, where you had within subjects manipulations, but only 1 observation per person per level of the within subjects. So I'm curious what would happen if instead of giving the full data to the hierarchical model, what if I gave just the means, the cell means, to the non-hierarchical model? How would that affect the inferences? Let me go grab the next line. Oh, no, it's opening it in something else. I have 2 RStudio sessions open, one on this side, and it is... Okay. So that's the sampling the hierarchical model prep for the non-hierarchical model. Okay, so I just pasted from the code we had from before when we did the repeated measures with some between effects design. So it's not called dat long, it's called dat2. So we've got a new thing W now. It's labeling the within subject contrasts. Maybe could have called it W2. But so dat2 ID sex. That is good. Again, labeling each person, what sex they come from. And hopefully this the non. So everywhere I see a dat long, I'm going to put dat2. Triple check that that works. Yep. All right. So again, I've run it the hierarchical way, where I'm actually representing the data as it's coming in. This alternative way, I've now computed a mean per condition, and I'm just running the non-hierarchical version of the model. And I'm interested. My hypothesis is that we're going to have narrower credible intervals. We're going to be more certain about things when we actually give it all the data and let it see that there's measurement noise and it's of this magnitude, relative to when we actually effectively we take out its ability to see that there's measurement noise there when we collapse things to a mean, and therefore it can only assume that there's been perfect measurement happening, which should cause it to consider any variability it sees as it actually might be on the standard deviations that get estimated higher. We'll see what happens. Just double check what the names of the parameters were in this old style. Oh, it was the same thing. Okay, so coef means. So let's compare. Pretty similar in terms of the credible intervals on each parameter for the coef means. Pull up coef SDs. Oops. 50 to 66. And I'm actually going to have to rerun this one because I overwrote post. So I have to regenerate that. Oh, darn, I should have saved that. So that's going to take a minute or two. Well, my first hypothesis was incorrect. We didn't get any more confident by going the hierarchical route with respect to where the means of the population were. Let's see about the standard deviations and the correlations. Those might. My intuition is that those should become more confident, or at least the standard deviations. My hypothesis is that the standard deviations, the estimate for the standard deviations should go down, because what it previously would have seen as, with the hierarchical model, it can see there's variability associated with how the effect manifests from person to person. And then there's also variability attributable to noise. The one where we've just gotten rid of its ability to estimate the noise should erroneously see more variability from person to person than there actually is.
It's like the computer doing like a marathon.
Yeah.
Sounds like a fun person.
It's the computer that does things really faster.
Oh, yeah?
It takes only like 5 minutes to do the most basic.
Oh, really? Huh. All right. Okay, so having done that, and right, this X. Aha! Yes, I was right. Okay. Scroll way above. We estimated variability in the intercept between 94 and 124, variability in the effect between 50 and 66, by actually seeing. So we haven't changed the variability intercept that much, but the estimated variability in the manifestation of the effect has gone down. So if we're seeing that there actually is much more consistency from one person to another in the manifestation of the effect relative to when we actually couldn't see the magnitude of noise. So the hierarchical model is getting a more accurate picture of how variable the effect manifests from one person to another, and that's going to affect any sort of measure of reliability, or if you're just trying to predict like power for subsequent experiments, that sort of thing. You're going to have a more accurate estimate for that. Now, actually, I want to see the.
And that's because the other one was giving you like a blanket term for the variability?
It's because it didn't have. You didn't see the trial by trial noise. You just were collapsing that to a mean, and therefore, I mean, there's still noise in the estimates of those means, but it no longer sees like the trial by trial data.
Okay.
So it can't estimate a noise parameter from that data. I'm going to do two things. First of all, I'm going to take a look at correlation. So what a core mat is what we called it. Dim names. Why? Right. Okay. So there's our correlation between intercept and effect in the hierarchical model. I'm going to say post h equals post. Of course, I've overwritten now the non-hierarchical model. Let me rerun that one, but that one should go really quickly. I'll call this one post h. Oh, that sucks.
A little like bomb.
Yeah.
There's nothing else except the start new session. Like there's no like cancel and letting like look for a second.
Oh, and as it tried to resume the session, it just crashed again.
Oh no.
I like it.
Come on. In theory, we could pause the video recording and scroll back to see what the values were. I didn't have a ton of stuff for today anyway, so I can put up with some. Yeah. Okay. But I am going to name things properly. So post h for that one, and oh, darn it. It didn't. Yeah, it didn't save any of the changes I made.
You make it look so easy. So.
Yeah. Okay. Well, this is going. I will add in that other stuff. which I can just copy from this other one over here. To one observation per cell. Okay. Okay, so get from her posterior. Oh, A and B? What? Oh, I opened up.
Fighting you.
I opened up the mixed analysis that we. This is not hierarchical. Yeah. There we go. Maybe we'll still have the changes. No, that's still there. Don't save. Go to the visualization stuff. It's just redundant from the other day. That.
Would you save as something else though?
Yeah, I'll run it at post h equals post. That'll work. All right, and that creates stat 2. All right, done sampling the hierarchical model. There's noise, there's the estimates of the coefficient means, there's our variability, and there's the correlation, collapse to mean per condition, generate a contrast matrix for within, contrast matrix for between, run the non-hierarchical model. So non-hierarchical runs faster, obviously, gets approximately the same sort of values for like the effects. Overestimates the amount of variability in A because it frankly can't see that there's measurement error in there. And I'm pretty sure that's about what we had for the other one. Yeah. I'll have to, on my own, I'll generate an example where there actually was I generated data When there's intercepts, there is a correlation between the intercept and effect to triple check that this isn't just the same because it's null in the first place. But yeah, so seemingly the difference is that the version of the model that estimates out variability without any ability between, or the version of the model that doesn't see the measurement error overestimates the amount of variability you expect to see in terms of those scores from person to person. One last thing I wanted to do with this is that in theory we could, and I'll just copy all this, I'll call it I'll call it H2 because we're going to run the hierarchical model on the collapsed data. Now, this is actually because I thought of it as the class was about to start, because I'm not actually sure I have a hypothesis as to what's going to happen. So we're going to deal with DAT2, DAT2, W2, W2, DAT2 value, and DAT2 ID, W2, and B2. So it's going to be modeling the data as having random error associated with each observation, but it doesn't see multiple observations to actually estimate that error from. Oh, I just overwrote the wrong thing. Copy this and then Control Z, because this was the run the non-hierarchical model, right? So, oh no, it was the right thing. Okay. Okay. This is what I want to change. H2. Okay. Like in theory, like if we were doing something like a maximum likelihood approach to doing this model, which would be non-Bayesian frequentist type thing, you wouldn't be able to estimate out. You wouldn't be able to get an estimate for noise for a given person because there's no noise in the actual, there's only one observation per condition per person to have. So you can't get a standard deviation out of that. But because we're in the Bayesian world and we actually have a prior on the noise parameter, it actually will allow you to do this. And I'm curious how close to the original model where you see noise it can get.
Paul, can you explain a little bit about the difference in just emphasized in the type of noise that the Bayesian approach can estimate versus the time frequentist?
Well, because, so with the frequentist tools, you try to estimate you have a model and you try to get out the,
I have a more specific question in mind.
Yeah.
Maybe that'll help. What if we compared maximum likelihood ratio model with one where you use the subject's random slopes? Well, the other one where you only have random intercept. Would that be getting at that type of noise or something different?
no, even different from that. Yeah, that's something I kind of talked about a little bit the other day. We're not going to get into even bothering with models that limit the random effects. So whenever we have something like a subject, we're always going to allow them to have their own intercept and their own effect and a possible correlation between the two. There are more restrictive models that say there's variability amongst people in the intercept, but not in how their effects come about. And that, makes things more computationally easy to do, particularly for really big models with lots of predictors. But we won't need... That helps things computationally when you're in sort of a frequentist world, but we won't need that help in the Bayesian world. And it's frankly a somewhat untenable sort of hypothesis to assert that there's zero variability amongst people in the manifestation of an effect. We won't bother with those. So we just fit a model. We took the just means data, means per person per condition, and still tried to fit a hierarchical model to it. Let me compare to when we actually had. So fairly similar posteriors on the coefficient means. Interesting. So there's the posterior on the variability of coefficients from one person to another. And if, we've actually got really terrible effective sample size on the amount of noise there is from one person to another. So I really wouldn't actually trust this very much. All right, fine. I'm not going to bother rerunning it with much higher effective or with much higher iterations to bump that up to then answer this question. I might do that on my own and report back. My guess is that you're going to get a better answer still than if you model it the means with that hierarchical model, so that it's told to still try to estimate error, than if you just do the straight up repeated measures. But I'll get back to you on that.
Is there a particular reason that effective sample size is so much lower than the other one?
Well, it doesn't have the ability to see a given effect. So it's partly about how effective sample size is computed, but it doesn't have the ability to see the error at a given person. You can't compute the standard deviation for a given person. So it's just kind of making guesses. Yeah.
Okay.
I'll do a little bit more exploration and report back to you guys on that one. Okay. So that was just a little bit of exploration of what sort of how hierarchical models might relate to repeated measures models, where you don't have the multiple observations per condition. And I find often people will actually pretend to have repeated measures data when they actually have hierarchical data, in which case they end up collapsing things to a mean. And I want to illustrate that you can get slightly different, and depending on what you're interested in, incorrect answers when you collapse things to a mean, when you throw away information like that. Now, the means, the coefficient means, didn't change. And so if you're only interested in main effects and things like that, or only interested in whether an effect happened or not, you don't care about how reliable that effect is from one person to another, or how much variability in the population there is in that effect, then you can go ahead and use just the standard repeated measures. However, if you are interested in things like reliability or the consistency with which a given effect manifests from one person to another, and your data is hierarchical, you want to actually model it as hierarchical. I'll probably next time bring in an example of going back to the hierarchical binomial example and showing how you can actually, that's a scenario when you've got binomial data where you can definitely make wrong inferences even on the coefficient means. If you treat it as non-hierarchical, so you collapse things to a proportion and then do a Gaussian model on the proportions, as is very common. There's other things, though, you can do with the hierarchical model that are very useful that you can't really do with if you collapse things to a mean and then model them as a just a repeated measures model. So I'm going to bring up a new project, new folder in here, HMGH. The H stands for heterogeneity. This is going to be heterogeneity of, heterogeneity of measurement noise.
You know, like heterogeneity versus homogeneity.
Sorry?
Like when the opposite of that.
Yes, you're right. So these